Hello guys, I'm a teacher Olimboka Nsujuga Masame. Welcome to Olimboka Physics. We've given the questions concerning refractions of light in a plane surface. It says 2.3.2, question number 4 from TIE. Okay, we have given the velocity or the speed of light in water and in air respective, as you can see here below. I will use this question to derive the refractive index when of given pair of medium by using Huygens constructions, and also with using in such constructions to show how critical angles occurs and the general formula to calculate to find the critical angles between the pair of media. Okay, Huygens constructions is just a geometrical constructions that use the knowledge of earlier wavefronts to determine the positions of the new wavefront at some instant. It's postulated as here below. All points on a given wavefront are taken as point source for the productions of the secondary spherical waves, called the wavelets, that propagates outwards through a medium with the speeds characteristic of the waves in that medium. After some time's interval has passed, the new productions in the new position of the wavefront is surface tangent to the wavelets. After just reads these postulates, let us see from the diagrams below how we will just understand some lines here. Here we have a source. This is our main source, and this source transfer radial the energy of the wave, the energy from the source radially to the ends and or to the destinations. This source is let assume is a light source that will have some spherical wavelets, and this is spherical wavelets as three spherical wavelets, which will act as the point sources. Hence, we have 3 point sources: the one for the first wavelet, middle, and the last. Each point source produces a new wavelets. This new wavelet is just called a Huygens wavelet, and each point source producing a new wavelet with a characteristics of waves in that a particular media. But after certain time intervals, each new wavefront we will have swept a distance d for a particular media, and this is how we can determine the positions for each new wavefront for a particular media or for a given media by drawing the line tangent to each spherical wavefront. And for the spherical wavefront is the line tangent to the spherical wavelets, and see you have wavelets here. Remember that a new spherical wave front will be obtained after some time intervals, and this new wave front is called a secondary, the secondary spherical secondary waves. Now, after understanding this concept of Huygens postulates, let us see the Huygens constructions to just prove the Snell laws. Snell laws is just state that the ratio of sign of incidence to the sign of refractions is constant. It is constant for the given pair of media. Here we have two media, as from our questions. We have air and water media. We assume here light comes from air media to water media. that is medium 1 and medium 2. And for the second case is when we assume that light comes from a water media to air media. This is media 1 and media 2 respective. Okay, we will use these two diagrams simultaneous just to obtain the general formula that proves the Snell's law. Okay, incidence angle is always from normal to the incident ray, and the refracted angle is always normal to the refracted rays. That is where we can get the refracted angle. Now we have a refracted angle here, and here it is a 90 degrees. As you see, this normal is 90 degrees. Now we have 90 degrees minus r, and finally here we'll have r. And for the upper triangle in a medium 1, we have incidence here and here, because this normal is 90 degrees, this is 90 degrees minus I, and this is I, and this is tangent also. Okay, the line drawn from a first spherical wavelet at point O and the second spherical wavelet at point A form a plane wavefront, and also this point O act as a point of disturbance, that's our point source, to produce a spherical wavelet at point B. This spherical wavelet at point B take a displacement which is at a media 2, and this is also a new displacement that is produced by a point source A. It is taking a certain displacement from A to D, hence this D acts as also a new point source for other spherical wavelets. Okay, here we'll have a plane OA, OD, which act as a new point source, and here a tangent line from B to D forms or give us a secondary wavefront, that is a plane secondary wavefront, and this plane secondary wavefront is it is seen as comes from a ray OB and ray AD. Remember from here, the instant of time taken for a displacement OB and AD for the secondary wavelets that form the secondary wave front is the same as according to the postulate, that after some time interval has passed, the new position of wavefront is the surface tangent to the wavelet. Now the new position of wavefront at the same time interval is as you can see, a BD. This is a secondary wavefront, and this is a primary wavefront, and act as a point source for this secondary wavefront. Okay, after understanding that, let us see how mathematically we can find the sign of incidence and the sign of refracted for the first case, as you can see here, and this is sign of incidence and sign of refracted for the second case, as you can see here. Okay, we know that a displacement DA and OB and OA and BD as the wavelengths for the particular media. Now when for a case of air to water, our ratio is a refractive index of water divided by refractive index of air, and is equal to a sine incidence to sine of refracted, as stated by Snell's. And now we have this ratio where the dA is equal to a wavelength 1 for the medium 1, and the OB is equal to wavelength 2 for the medium 2, and for this case it's just a reciprocal of what is stated here, as you can see here. Okay, now the displacement is equal to CT for the medium 1, and displacement for the medium 2 is equal to VT. Okay, this is velocity for the medium 2, velocity for the medium 1, which is less media than this medium 2. time because is of the, as can see here, this time is cancelled out because this is secondary plane wave front reach at a point B and D at the same instant, and this same instant is equal to the same time interval, that is change in t. And this is rays OB and rays AD, which are perpendicular to the tangent of the spherical wavelets, reach at this new wavefront, plane wavefront, at an instant or at the same time interval as postulated by Christian's Huygens. Okay, that's why this time t and this time t is cancelled out, remaining with ct for this case, and also for this case BD. Remember, BD is of medium 1, hence it is wavelength 1, and OA is of medium 2, and hence wavelength 2, which is equivalent, or which is equal to velocity time of medium 1, that's the velocity of denser media, which is Vt, divided by a velocity of medium 2, which is less dense medium air, which is Ct. Remember, this T also is this secondary wave front that is AD will be at this position after some time interval. Hence, this BD and OD reach at this plane wavefront AD is same instant. And now time and time is cancelled out. Now it is V divided by C. Remember, V is for the angle of sign of incidence, which is within the same media, the medium 1, and C is corresponding to the angle of diffraction, which is corresponding to the same media, medium 2. C for the medium 2 and the refracted angles for medium 2. Don't forget this arrangement. The arrangements are very, very same. Even for this first equations, incidence is proportional to its wavelengths for a particular medium, and refracted is also proportional to the wavelengths for the particular media, which is medium 2, which is also corresponding to this ratio of velocity. Okay, now for a full general formula, we'll have the same general formula, just for refractive index for the medium 1, incidence for the medium 1, which is equal to refractive index for the medium 2, sign of incidence for the medium 2. This, remember, this incidence 2 is equal to refracted 2, the refracted angle, okay, which is equal to constant, and the same as for the C cases, despite that this cases is from water to air, which we know that this ratio is defined as ratio for air divided by ratio for water for a pair of for a media. This is and now, because we know refractive index for air is approximately to 1, and we'll have the reciprocal here when you have one media is air. Okay, now for the first equations, you can see we've given the speed of light in air to speed of light in medium. Now the ratio, the formula, and the final refractive index is 1.07. And for the second case, we have to find the refracted angle when we have a new angle of incidence. But remember, for the same media, which is air to water, now we will use the refractive index, which is of the same media, and this is a value of incidence angle. Now our refracted angle is 27.86 degrees. For the case of critical angle, the condition of critical angles when is fulfilled by this second case. It's when a light wave moves from a denser media to less denser media. As it's moved from less denser media to less denser media, the angle of incidence is increasing. Let's say that the source of light here is moving away somehow in such a way that the angle I is increasing. It's just increasing away from the normal until become equal to critical angle. and hence this this refractory angle increasing until it is it is 90 degrees, and the refractory rays is on the surface of the media boundary between medium 1 and media 2. And at that time is as we draw here, this is 90 degrees, and this is very bright, and weak rays is also seen, that is below the dense, is within the dense media. And now at these conditions where I is equal to C, because this will apply just the same general formula, whatever, because we just regard the arrangement of medium with their respective angle. For here is that when we take this as medium 1, then we will have refractive index 1 here, and when take this as medium 2, we will have a refractive index 2 with the angle of refractions, that is incidence 2, or which is equal to R, which is 90 degrees. Now by that arrangement we substitute always. Here we will have a critical angle which is equal to a refractive index of air times a sine of 90 degrees divided by refractive index for a given media. Remember, sine of 90 degrees is equal to 1, and C, therefore the arc sine, or the sine, the inverse of sine of reciprocal of this refractive index is equal to critical angle. Thanks for watching. Please like, share, comment. Don't forget to subscribe this channel for more videos like this one. Thank you.